Okay, now we roll a ball down two ramps in the manner that you're accustomed to. The ball rolls directly from one ramp onto the second without speeding up or slowing down at the interface between the ramps. It rolls smoothly from one ramp to the next. And it takes 8 half cycles from rest to go down the first ramp by itself, and then to go down both ramps starting from rest, it takes a total of 12 seconds. The ramps have equal lengths, so the second ramp has a length of 12 domino lengths. Each ramp has a length of 12 domino lengths. So if we want to analyze the motion on the first ramp, how do we think it through? First, we identify what we know. From rest, meaning V naught equals 0, we go length of the ramp, 12 domino lengths, in 8 half cycles, which I'm going to abbreviate HCY. What can we determine from this information, or do we need to go to the equations? And of course, you're free to go to the equations if you want to, unless you're asked to reason it out, but we're going to reason this one out because it gives us more insight. Okay, and this one is amenable to reasoning out. So what can we combine here? Well, we can't combine V naught with anything and get anything useful because we don't know VF. But we can combine delta S and delta T. How do they combine? Well, they are related. First of all, you're probably going to stop and think. So, let's talk about a minute how we'd use intuition. You're going to want to write average velocities delta S over delta T. Now you might accidentally write final velocities delta S over delta T, or delta V equals delta S over delta T. Really easy to write a delta V here instead of a V bar. So what you need to do to check and make sure that what you want to do is correct is, and let me also say, it's important to identify what you're getting. Some people will just write down delta S over delta T and calculate it without identifying what that is. Then later in the problem, they'll use that and they'll misidentify it because they didn't identify it correctly the first time. So, now, how do we use definitions to verify that this is a correct relationship? Well, what definition is embodied in this relationship? It's the definition of average velocity, which is the average rate of change of position with respect to clock time. And that is change in position divided by change in clock time. Delta S is the displacement, the change in position. Delta T is the change in clock time, and that does give us average velocity. And the definition also gives us this triangle here that I just kind of jotted down for reference, and maybe can't read it and maybe couldn't read it in class. But it's just the triangle with V bar, delta S, and delta T. Some people are still having trouble understanding what those triangles tell us. Well, what a triangle means is that if there's 3 quantities, and if you know any 2 of them, you can find the third. So that we've got this triangle, and here's the relationship that comes out of the definition. So this triangle tells us that the definition relates average velocity, displacement, and time interval. And the result of the definition is that we have the equation, average velocity is delta S over delta T. So clearly from this equation, if we know any 2 of these 3 quantities, we can solve for the third. And that's all this triangle is representing. Okay, well, V bar is delta S over delta T. That's going to be your 12 domino lengths divided by your 8 half cycles, 1.5 domino lengths per half cycle. And once you're here, everybody's in pretty good shape, but some people are not writing down units at every step, and I want to see them at every step in every calculation. It's not because I love seeing them, although it makes a lot more sense to me if I'm seeing the units, but I know what I'm looking for. But it's got to make sense to you, and you've got to put those units in there because that'll force you to think a little more about what you're doing and what everything means. Okay, well, then what? Well, then we come over here and use the straight line property of the V versus T graph, which tells us that the average velocity is the average of initial and final velocities when the V versus T graph is a straight line. We use this property. Now, some people are going to want to double the average velocity. I've seen a lot of doubling of average velocities. Okay, well, we used that earlier with the special condition that applies if the initial velocity is 0. Now that's the case here, so you would be free to do that, but I'm not going to do it that way, and I really don't want you to do it. I won't penalize it if you do it, as long as you verify that the condition that the initial velocity is 0 is valid, that it applies in the situation. If the initial velocity really is 0, I'll tolerate that, but I don't want you to use that, because just like cancellation and some other things, people just get in habits and misuse it. Also, it's not the way you reason it out in most cases. Okay, so anyhow, well, what am I talking about? Well, we know that average velocity is Vf plus V naught over 2 from the straight line property, and that the initial velocity is 0, so that the Vf plus V naught over 2 is Vf plus 0 over 2, which is just Vf over 2. That's equal to V bar, so that Vf is double the average velocity. That's going to be double 1.5 domino lengths per half cycle, or 3 domino lengths per half cycle. So we do end up doubling the average velocity, but we know now, having gone through this rigorous process, that that's valid. And that you can see how that follows if the initial velocity is 0. If initial velocity wasn't 0, we would not end up with twice the average velocity, would we? So go through this process to be safe. Anyhow, we get the result, and basically what we've done at this point is we said, okay, average velocity is delta S over delta T, 1.5 domino lengths per half cycle, and the final velocity, well, the initial velocity is 0, so final velocity should be double the average velocity. That's what our intuition, our experience will tell us. Going back to the definitions and the properties, we verify that it's so. Okay, then we can use definition of delta V to find delta V, just Vf minus V naught, and that's 3 domino lengths per half cycle minus 0, 3 domino lengths per half cycle. Okay? And why would we want delta V? Because we're trying to find the acceleration. Definition of acceleration, average rate of change of velocity with respect to clock time is change in velocity divided by change in clock time, which is delta V over delta T. And we have this triangle, the delta V, delta T, A triangle here, just indicating to us in a visual manner that if we know 2 of these things, we can find the third. Here's the equation that we would use to do that. Up here, incidentally, I drew the delta V triangle. V naught, Vf, delta V, obviously, those 3 are related. Okay, just by this relationship. Okay, so now we found delta V. We know now that acceleration is delta V over delta T. We checked that with the definition, so we proceed to use it. 3 domino lengths per half cycle, that's our delta V. Delta T is 8 half cycles. 3 divided by 8, well, it's 3/8, which is 0.375, and we might not have all those significant figures, of course, but it's 0.375 domino lengths per half cycle squared. There's our acceleration on the first ramp. Now we analyze the second ramp. Now it should be very clear, and I'm not going to detail it here, that if it takes 8 half cycles to get down the first ramp from rest, 12 cycles to go down the first and second ramp from rest, that the difference, the 4-cycle difference, or four half cycle difference, is the time required to go down the second ramp. So on the second ramp, what do we know? Okay, well, we know its length, so that the displacement on the second ramp is 12 domino lengths. I keep wanting to say deciliters, because that's really what D would stand for. But anyhow, okay, delta S would be 12 domino lengths, length of the ramp. The initial velocity is equal to the final velocity from the first ramp, because the ball rolls smoothly from the first ramp to the second. And the end of the first is the beginning of the second, so that it's going to have that 3 domino length per half cycle velocity at the beginning of the second ramp. So analyzing the motion on the second ramp, we have this. Then time interval is 4 half cycles. So we have this, this, and this. Now I'm not going to be as I'm not going to write out the triangles and stuff like that. I'm just going to say the definition, ... You know which definition, and if you don't, you need to practice. It's a definition of average velocity. Tells us that the average velocity is delta S over delta T. and that's 12 domino lengths over 4 half cycles, which is 3 domino lengths per half cycle. Now, at this point, somebody observed, well, that's the same as the initial velocity, so the final velocity is going to be the same. And that's perfect intuition about how the initial, average, and final velocities relate. But I'm going to carry this through with all the details, because the details could easily be changed. For example, if this was, instead of 4, this was 3 half cycles, okay? Then you would not get an average velocity that was equal to the initial. Now, in an actual experiment, you can get things that come out this way, okay? The experiment appears to show that the second ramp has a 0 velocity, at least it will when we get down to the final, or 0 acceleration, which is what we're going to get when we get down to the final step here. And we're pretty sure that isn't the case, because we can kind of hear the ball speeding up when it's on that second ramp. So our data is obviously a little bit flawed, but a slight change in the data corresponding to a slightly more accurate observation could lead us to a really good conclusion. Okay, now we've determined that the average velocity is 3 domino lengths per half cycle. The straight line property tells us average velocity is final plus initial over 2. So, well, that means if we find VF, because remember we're trying to find acceleration, we know the initial velocity, we're going to need to find the final velocity in order to get the acceleration. So we want to get the final velocity. We solve this for VF. Multiply both sides by 2, we get 2 V bar. Subtract V naught from both sides, we find that VF is 2 V bar minus V naught. And that's then going to be 2 times your 3 domino lengths per half cycle minus 3 domino lengths per half cycle. Well, when you do that, 2 times 3 is 6, subtract 3, you get 3. It's all domino lengths per half cycle, so these are like terms. So you're going to end up with domino lengths per half cycle, and you're going to end up with 3 of them, just as we pretty much knew was going to happen, since the initial and the average were both 3. The final is going to be 3. Then we want to find the acceleration. The definition tells us, okay, we reason through the definition. Maybe we write down the triangles if we find that helpful. We have the acceleration is delta V over delta T. And, of course, delta V is final minus initial velocity, which is 3 domino lengths per half cycle, minus 3 domino lengths per half cycle, divided by the delta T, the 4 half cycles. And in this case, we do get 0. Now, I'd recommend that you work this through, assuming that this was a bad observation. It really only took 11 half cycles, and see what you get for the acceleration on the second ramp. It's not going to be 0, but all the steps and all the reasoning will be completely identical, and all the reasoning is there.